Hello, pre-algebra students. In section 3 of chapter 9, we're going to be multiplying and dividing monomials. Remember, a monomial means it's one term, not separated by an addition or subtraction sign. Multiplication is okay, it's still a monomial. Exponents, we learned yesterday, exponents show repeated multiplication. Okay, so that's how many times a number is going to be multiplied times itself. Repeated multiplication. So we're going to use the definition of exponents to help us remember the rules for multiplying or dividing monomials. For example, 3 squared times 3 to the third. Well, 3 squared means 3 is multiplied times itself twice, times 3 times itself 3 times. Well, you'll see here that 3 squared times 3 to the third, we really actually end up with 3 multiplied times itself 1, 2, 3, 4, 5 times. All right, there is a shortcut for multiplying powers of products. When you have the same base, like we had 3 times 3 here, example a to the m times a to the n, it does not matter what our exponents are. The result is going to be whatever your base is, a for our rule here, to the power of m plus n. This is a shortcut. You could always do the long way where we did it up above, but let's check the shortcut. 3 to the power of 2 plus 3. It would also give us 3 to the fifth. So that's much quicker than writing out 3 times 3 times 3 times 3 times 3, so on and so forth. So multiplying powers with the same base, remember a here is our base, you're just going to be adding the exponents. So when you're multiplying, exponents add. That's what you need to remember. That's the shortcut. So let's look at example number 1. Find each product and express using exponents. Now the old-fashioned way, if we go back, is to say 3 times 3 times 3 times 3, that's 4 times. Then we can change colors and say then 3 times 3, we're going to do it 6 times. And my dots aren't showing up, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I end up with 3 to the 10th. Well, I don't know about you, but I've got better things to do than to sit around spreading 3 everywhere. So let's go use our shortcut. 3 to the power, since it's the same base, they both have a base of 3, to the 4 plus 6 would have given me 3 to the 10th much quicker. So whenever you have a 7, it's understood to the first power because it's not to the 0 power. We're going to talk about that in just a minute. So it's to the first power, because it's only there, you would only write 7 one time. Here I wrote 3 4 times, so if it's just a 7, I'm going to write it one time. So to do our shortcut, it's 7 to the power of 8 plus 1, so it would be 7 to the 9th. That's the quickest way to get there. Know that you can always go the long way around if you want to, but my job is to show you that there are shortcuts. All right, here we have y. Again, this is understood to the power of 1, so you can write it out, y times y times y times y times y, and you have y to the 5th. But the quick way to do that is to say 4 plus 1 makes 5. Here I have 3 times p times p times p times p times, because parentheses right there just means multiplying, and I've got a negative 2, so I always put my negative in parentheses so I don't forget the negative goes with the 2, p times p times p. So if you count up your p's, I have 4, 5, 6, 7 p's, and 3 times negative 2 is negative 6. So that's going to be our final answer. Using the shortcut, you would say 3 times negative 2 is negative 6, p to the 4 plus 3 would have also given me the same answer of negative 6p to the 7th. All right, let's talk about what we're going to do for dividing monomials. Here I have 5 times itself 6 times. One more, okay, over 5 times itself 2 times. Now, hopefully, at this point in our mathematical career. We know 5 cancels with 5, leaving us with 1. And this 5 cancels with 5, leaving us with 1. So in my denominator, I have a 1. On top, I have 5 times itself 4 times. Okay, so we would just write that answer as 5 to the 4th. You don't write the 1 is understood. Okay, that's the long way. Let's look at a shortcut. The quotient of powers property says when you have the same base and you are dividing by the same base, then you can just say it's a to the m minus n. Notice when we were multiplying up above we added. When you're dividing, you are going to subtract exponents. Okay, divide powers with the same base by subtracting exponents. Let's go up here and check to see if we agree. Let's get another color here. Go back to purple. So 5 to the 6 minus 2. 6 minus 2 is 4. We would end up with the same answer using the shortcut, and that's much quicker than writing out all of our multiples. So let's go to find the quotient. I'm going to do the long way just to show you how ridiculous it is. I've got to write 4 11 times. So it's 4, 5, 6, 7, 8, 9, 10, 11 times over 1, 2, 3, 4, 5. Cancels, 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 cancels. I should have canceled 1, 2, 3, 4, 2, 3, 4, 5. I did. I canceled 5 4s. So how many 4s do I have left? I have 4 to the 1, 2, 3, 4, 5 to the 6th power. I don't know about you, but if I knew that I could just say 4 to the 11 minus 5 and get 4 to the 6th power, I'd rather do this all day long than to sit there and write out all my 4s. So I'm going to do the shortcut on B. This is understood to the first power, so it's simply going to be x to the 12 minus 1, which is x to the 11th. Boom, that is so much quicker. All right, let's look at this table below. It shows the approximate height of some clouds. Okay, maybe some of you love studying meteorology and looking at the heights of clouds. About how many times higher are some high clouds than some low clouds? So here are high clouds and here are low clouds. And we're doing a comparison of how many times higher they are. So usually when we make a comparison, we make a ratio. We're comparing high clouds to low clouds. So using my information in the chart, high clouds were 2 to the 13th power. Low clouds are 2 to the 10th power. So to do that comparison, since it's a division problem, I simply say 13 minus 10. So it's approximately 2 to the 3rd power would be the comparison. And since it asked us how many times higher, you can go ahead and say 2 times 2 times 2, 3 times, which gives us approximately 8. So 8 times higher. Okay, so it's just nice to see how you can make practical application of the information you've just received. You can always do the long way, but man, compare the long way to the shortcut, compare the long way up here in multiplication. Would you rather write out all your 3's or just say 4 plus 6? I hope you will embrace the shortcut. Okay, so now we're ready for section 4, where our exponents are going to become negative. But first, let's just review what we just talked about. So we have x to the 3rd over x to the 5th, which cancels, 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 which means there's understood 1 on top. 1 over x squared. That would be the result of doing the long method. Using our shortcut from section 9.3, we know we have the same base, so we could just say 3 minus 5. We are subtracting integers here where the bigger number is negative. So remember, it's like saying plus a negative 5, so we subtract and keep the sign of the larger. So it's x to the negative 2. X to the negative 2. Now that's weird. You realize that we're not used to having a negative exponent, and you are correct. So we have So what I want you to realize is that 1 over x squared is the same thing as x to the negative 2. You know we're right because we did it the long way. And so because the negative probably threw some of us off, not anticipating a negative exponent, what you need to realize is that these two values are equal. And that leads us to our negative exponent rule. When you have a to the negative n, it's the same thing. It is equal to a to the n. They're the same value, and we've shown you here at the beginning why that is true. Likewise, 1 over a to the negative n. We don't like the negative exponent, so if we bring it to the numerator, when you bring it up, it's going to become a positive n. So what you need to realize, it's like a magic wand. And that's what these are supposed to be my magical symbols here. The division bar is like a magic wand, and when you cross over the magic wand, it changes your exponent sign. So if you have a negative exponent and you go to the denominator, it becomes positive. If you take your negative to the numerator, it becomes positive. All right, so let's practice with some examples. 3 to the negative 4. 3 is understood over 1. So if I go across the magic wand and leave a 1 in my numerator, it becomes 3 to the 4th power. And all they've asked us to do is to write these with positive exponents. So I'm finished with A. B has the same situation. All numbers are understood over 1, so there's my magic bar. When I take it to the denominator, I need to leave a 1 in my numerator, and it becomes 1 over m squared. Now it wants us to write these using negative exponents. Okay, well, first I've got to make it an exponent. So 125, if I do the prime factorization, 5 goes 25. And so it's 1 over 5 times 5 times 5, which is 1 to the over 5 to the third. So if I make it a negative exponent, I take it across the magic bar. There's an understood 1 left in the denominator, and 5 becomes to the negative 3. And I don't like to leave a 1 because that's understood. That's very elementary, and we're about to be in high school. So our final answer is 5 to the negative 3. All right, if you recognize that 125 is 5 to the third, then you didn't have to work it all the way out, but I wanted to show all of my steps. All right, since this one's already 8 to the 4th, I'm just going to take it across the magic wand and make it 8 to the negative 4th. And again, the final answer is 8 to the negative 4th. We do not need to put the 1 in the denominator. All right, for the sake of time, we're going to omit number 3. We may come back to it later, but let's evaluate 16r to the negative 3. So we're using substitution here. In place of r, we're plugging in a negative 4. I don't even know how to do negative 4 to the negative third power, so I'm stumped. What I have to do is use my knowledge about how to convert a negative exponent to a positive exponent. So it ends up leaving 6. 6 is still staying on the top, on the numerator. And negative 14. Now my negative 4 doesn't change symbols. The only thing that's going to change symbols because of our magic wand is the negative 3. It becomes a positive 3. So it's still a negative 4. So be careful. 16 over negative 4 times negative 4 times negative 4. You can punch that in your calculator. And since it's an odd exponent, it's going to stay negative. So 16 over negative 64, 16 goes into 64 4 times, and it stays negative. So our answer is negative 1/4. Now, whenever you have a number to a 0 exponent, the value is going to be 1. Any number to the 0 power equals 1. And turn your paper over. I'm going to show you why that is. At this point, we all should know 2 over 2 is 1, x over x is 1. Okay, using our shortcut, this is understood x to the first, and we said when we divide, we actually subtract our exponents. Oh, so that gives us x to the 0 power. That is why anything to the 0 power equals 1. So what is 5,673 to the 0 power? Anyone? 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 You're right, it's 1. Have a great day.